Suppose a short audio burst contains two notes only 26 Hz apart. You want to know exactly when the burst begins, and you also want to separate the two pitches. Here is the catch. The time, frequency, uncertainty principle says one analysis window cannot do both arbitrarily well. To see why, we will build the Fourier transform from rotating complex numbers, derive the exact 1/2 bound for Gaussian widths, and then test two windows on a concrete audio signal. Start with a familiar fact. Several pure oscillations can add to one complicated waveform. Each oscillation has an amplitude, which sets its size, a frequency, which sets how fast it repeats, and a phase, which sets where its cycle begins. Fourier analysis reverses this construction. Given the sum, it asks how much of every possible oscillation is present. The word frequency here means a coordinate in a different description of the same signal, not a new physical object hidden behind it. The cleanest oscillating atom is the complex exponential e to the I omega t. Here I is the number whose square is -1, t is time, and omega is angular frequency in radians per second. Euler's formula says this rotating arrow has cosine as its real coordinate and sine as its imaginary coordinate. Complex notation packages both real oscillations and their phase into one object. It also turns differentiation into multiplication by I omega, which will matter in the uncertainty proof. To test whether a signal x contains angular frequency omega, multiply x of t by e to the -I omega t and integrate over all time. The negative rotation unwinds a matching component, so its contributions point in one direction and accumulate. A mismatched component keeps rotating and largely cancels itself. The result is x hat of omega, a complex number whose magnitude measures strength and whose angle records phase. This is the continuous analog of projecting a vector onto one basis direction. We now lock one convention. The forward transform is x hat of omega equals the integral of x of t times e to the -I omega t dt. The inverse is x of t equals 1 over 2 pi times the integral of x hat of omega times e to the +I omega t d omega. The forward equation analyzes. The inverse synthesizes. The factor 1 over 2 pi belongs to this angular frequency convention. Move it elsewhere, and the numerical uncertainty constant must move with it. The transform is complex. Its magnitude tells us how strongly a frequency appears, while its phase tells us how that oscillation lines up in time. For a real-valued signal, positive and negative frequencies carry conjugate information, which is why magnitude plots often look mirrored. If you discard phase, many different time signals can share the same magnitude spectrum. Exact inversion needs both. In this lesson, width will be measured from squared magnitude because squared magnitude behaves like an energy distribution. Take x of t equal to exp of -t squared over 2a squared, where the positive number controls the time scale. Completing the square in the transform integral gives x hat of omega equal to a times square root of 2 pi times exp of -a squared omega squared over 2. So a wide Gaussian in time is narrow in angular frequency, and a narrow one is wide. This reciprocal scaling is exact, not a sketch. The Gaussian's special shape survives the transform. To state uncertainty precisely, first divide squared magnitude by total energy so it integrates to 1. Let t0 be the mean time under the normalized density absolute x of t squared. Define sigma t as its standard deviation. In frequency, normalize absolute x hat of omega squared using Percival's factor 1 over 2 pi. Let omega 0 be its mean, and define sigma omega as that standard deviation. These sigmas measure root mean square spread, not compact support, and not the width of a hand-drawn box. Shift and modulate the signal, so both means are 0. Assume x is differentiable and decays fast enough that boundary terms vanish. Integrating the derivative of t times absolute x squared gives 0. After rearranging, half the energy is at most the absolute value of the inner product between tx and x prime. Cauchy, Schwarz bounds that inner product by the norm of Tx times the norm of x prime. Parseval then turns the derivative norm into the frequency-weighted norm. Dividing by energy yields sigma t times sigma omega, at least 1/2. Where can equality occur? Cauchy, Schwarz is tight only when the two functions it compares are proportional. Here that requires x prime of t to equal minus ct times x of t for some positive constant c, after centering and removing a carrier frequency. Solving this first-order differential equation gives a Gaussian. For our parameter a, sigma t equals a over square root 2, and sigma omega equals 1 over a square root 2. Their product is exactly 1/2. The same mechanism appears without the proof. If y of t equals x evaluated at t divided by a, then y is stretched in time by a. Its transform is a times x hat evaluated at omega, so the frequency axis is compressed by 1 over a. Reverse the scaling and time narrows while frequency broadens. Multiplying the heights changes energy, but not the reciprocal relation between the two widths. A signal cannot beat uncertainty merely by being louder. An ordinary Fourier transform mixes all times together, so it can tell us which frequencies occur but not when they occur. To ask a local question, choose a window W and center it at time tau. Multiply the signal by W of t minus tau, keeping mostly the neighborhood around tau, and transform that product. A short window gives a precise time neighborhood, but multiplication in time has a consequence in frequency that prevents free precision. The transform of x times w is 1 over 2 pi times the convolution of x hat with w hat. Convolution means that each spectral value is spread using the shape of the window's spectrum. A narrow window in time has a broad transform, so it smears nearby frequencies together. A long window has a narrower transform, so it separates frequencies better, but it mixes a longer interval of time. This is the operational face of the uncertainty principle in signal processing. Slide the window center tau across the signal and repeat the local transform. The result is the short-time Fourier transform. S of tau comma omega equals the integral of x of t times w of t minus tau times e to the minus I omega t dt. A spectrogram displays the magnitude or power of S as color over a plane whose horizontal coordinate is time and vertical coordinate is frequency. Each column is one windowed spectrum. Our synthetic burst contains a 440 Hz tone and a 466 Hz tone, active from 0.65 to 1.35 seconds. With a 16 millisecond hand window, the spectrogram finds the on and off edges sharply, but the two pitches merge into one broad band. With a 256 millisecond hand window, two horizontal ridges separate, but energy leaks before and after the true edges. A larger display FFT only samples the picture more densely. It does not undo the window trade-off. The Fourier transform is a change of coordinates from time to rotating complex exponentials. Its inverse rebuilds the signal. Gaussian widths show the exact reciprocal scaling and integration by parts plus Cauchy. Schwarz proves that every suitable non-zero signal obeys sigma t sigma omega at least 1/2 in our convention. In practice, choose the window to match the question, short for transients, long for nearby steady pitches. Wavelets and multi-resolution methods exist because real signals often need more than one scale.